Good morning, friends. Yesterday night we had indeed a very vibrant cultural program. I hope everyone enjoyed it. Professor Siddiq, dear friends, first of all, it's a great pleasure to be here in this very exciting workshop with some of the most informative presentations seen during the last 2 days. At the outset, I would like to thank Rajiv for giving me this opportunity to present on behalf of the CIMMYT's Global Maize Program team, which I lead. The emphasis of my presentation will be mostly on climate resilient maize development and delivery for the tropical and subtropical regions of the developing world, what progress we made both through conventional breeding and market-assisted breeding, and what challenges remain in this regard. Recently, when the Global Millennium Project conducted a survey on what are the 15 most important challenges facing humanity, these are the ones that came up right on the top. Sustainable development and climate change featured as the #1 priority by a vast majority of respondents that participated in this survey. Closely followed by clean water, population and resources, democratization, long-term perspective, global convergence of information technology, the big data analysis, the rich-poor gap, health issues, the capacity to decide, peace and conflict. So these are among the top challenges that are highlighted by this very important survey. There is no doubt sustainable development and climate change has to be majorly approached through not only through mitigation but also adaptation to climate change. In that regard, maize is a very, very important crop because it's a food feed for millions of poor in the developing countries. At least 125 out of almost 170 countries that grow maize today are from the developing world. And maize accounts for 15 to 56% of the total calorie intake of the people in the developing countries. So it's really important for food security, coupled with the fact that it's food to 900 million poor people who survive on less than $1 to $2 per day. And maize importance in Asian cropping system is growing tremendously. In the last 10 years, the region has experienced almost 4% annual growth rate, much higher than many other crops. And this is widely possible because of the multifaceted use of maize. Maize in Asia is hardly China is the #1, almost 35 million hectares. It's the #1 crop in China, almost equivalent to that of what you see in US. But at the same time, maize in South Asia and in sub-Saharan Africa, which are the two major hunger hotspots, is particularly vulnerable to climate change. The analysis done by David Lobel and his team from has clearly highlighted what is the threat of global climate change on various crops, and maize is one of the major crops that features as one of the hardest hit ones from the South Asian and sub-Saharan African perspective. But adapting maize to the climate change scenario requires not only stress-resilient and input-use efficient varieties, but also designed diversification, efficient resource management, especially water, land, and energy, and appropriate policies. So what we discuss here during this 3-day workshop is only perhaps 25% of the complexity. There is 75% that still has to be approached through different lenses, different ways, coupled with the information, better information on future climates. Kadambo Siddiq was just mentioning about a major conference in Amsterdam dealing with this issue of how to adapt crops to climate change. So this is indeed the buzzword right now. But how do we indeed adapt crops to climate change? This can only be possible, first of all, through availability and intensive use of diverse and suitable source germplasm, coupled with long-term commitment. If CIMMYT's maize program today is highly successful in development and delivery of climate-resilient maize varieties, That's because of the fact that intensive investment of time and resources were made through 1970s. Almost 40 years of continued commitment to developing drought resilient and low nitrogen stress tolerant germplasm. That's what has paid rich dividends now and paying rich dividends and will continue to pay. One of the key stories behind this is constitution of populations like this, La Posta Sequia, which continues to yield excellent lines for various abiotic stresses as well as biotic stresses, mainly derived from a few populations that were widely available in Mexico. DTPY and DTPW are two major sources, again, drought-tolerant program, yellow and white, constituted by the physiology program led by Greg Edmeades in the 80s. And this constitutes almost 60% of lowland tropical, 20% subtropical, and 20% temperate materials. You can also see some of the most famous materials such as Suvan featuring as one of the important populations that went into the constitution of DTPY, besides Tuxpannosequia, Letente, Michoacan, and a range of CIMMYT populations developed by breeders since decades. Dr. Wassel, are you there still here? He is the one who constituted several of these source populations, which went into DTPY and DTPW. At the same time, the gene bank provides a tremendous resource for CIMMYT maize breeders as well as those in the NARS and SMEs throughout the world. The diversity of these resources is indeed staggering. Unlocking the functional diversity within this rich collection of genetic resources is a big challenge, but one that is being taken up with utmost intensity by our Seeds of Discovery team. I'm sure you heard about the presentation from Sarah Hearn earlier. This germplasm, can somebody recognize what is this landrace? Which is almost 35 to 45 centimeter long ears. This is the Hala maize, one of the world's longest eared maize. And you cannot see such kind of maize anywhere, and still preserved and still continues to be used by farmers in Mexico. At the same time, we all recognize the importance of what farmers want here. Farmers need varieties that not only yield well, but yield stably, especially under optimum as well as under the stress-prone environments. Not only performing well in best years, but also in the worst years, providing something to offer, something to eat. This can only be possible through a breeding strategy that combines well screening, intensive screening, not only under optimal conditions, but also under the managed drought stress conditions, random drought stress condition, low nitrogen stress conditions, as well as diseases that are based on regional priority. So CIMMYT's breeding strategy, therefore, revolves around intensive screening of our germplasm at different stages of testing against these important abiotic and biotic stresses, and then perform regional on-station trials on the best bet products that come out of this product pipeline, and move into the regional on-farm varietal trials where we compare, once again, a further distilled set of products against the best commercial checks available in the market. And those that pass through this entire intensive screening process actually go to the partners for nominations into the varietal release process and then finally release. So extensive field-based stress phenotyping network is fundamental to our efforts towards developing climate-resilient varieties, be it maize or any other crop. In sub-Saharan Africa, we have a very extensive managed drought and heat stress screening network, not only for conventional drought or heat stress, but also for the transgenic drought. CFTs, confined field trials, are established in Kibako in Kenya. Similarly, the nitrogen use efficient phenotyping network established through a project called IMAS, funded by the Bill and Melinda Gates Foundation, is one of the largest networks for low nitrogen screening anywhere in the world of any organization. This is not just made possible through CIMMYT's own efforts, but intensive involvement of both public and private sectors. 10 countries, almost 50 hectares of dedicated low nitrogen stress screening plots, capacity to grow at least 120,000 rows of materials at 21 locations contributed by public sector partners and 5 locations contributed by private sector partners. So involvement of the private sector is also essential, not just for delivery of your improved products, but right at the stage of establishing a strong stress phenotyping network. Gary, who is the architect of this particular project, is proud to be here in this audience to see this. At the same time, in Latin America, we do have a very strong phenotyping network comparable to the best of the partners from the multinational corporations, especially in Mexico. Almost 68 partners, including public and private, are part of this consortium to evaluate the products that flow out of CIMMYT's pipeline. And you can see these sites for lowland tropics as well as subtropics as well as highlands. Almost 155 testing sites. The number here is also the key. How strong and how wide is your network to derive products that can stably perform across environments and across these testing sites. That's how public sector has made huge progress. The private sector, the big private sector companies have made huge progress. And there is an intensive realization that this needs to be replicated also in the public sector. Heat stress phenotyping network is another major networks that we established recently through a project called Heat Tolerant Maize for Asia. 23 heat stress phenotyping locations stretching across South Asia, including those from Pioneer, from NARS in Bangladesh, India, Nepal, and Pakistan. Perhaps the largest heat stress phenotyping network once again, and very ably managed by Parvez Zaidi, who sits here in the ICRISAT campus in the CIMMYT India program. So that's the second most important part, is about establishing a strong and well-managed phenotyping network. The third most important part, again, where public and private synergies are possible, is devising the stress phenotyping protocols and selection criteria. We learned a lot from institutions such as Pioneer on how to do drought stress phenotyping, and I'm sure in the same way, the reverse way, the multinational corporations have also learned a lot through CIMMYT's stress phenotyping. And this has been, again, a major factor behind the success of the germplasm development. And a very clear and contrasting responses one can observe under well-watered conditions as well as under drought stress conditions. Also, not just establishing a site for drought stress phenotyping, but also carefully measuring what's the soil water profile through new tools and techniques. Coupling this crop responses data with the weather responses or weather patterns is extremely important for the success of phenotyping for drought stress. And the result of this is a very clear differentiation at the product level. You can differentiate using such a managed drought stress phenotyping a drought-tolerant hybrid from a drought-susceptible hybrid. Ultimately, that's the proof of your phenotyping, that you should be able to recognize, unravel the responses of your genotypes in a consistent and reliable manner with high heritabilities from these phenotyping sites. Hyderabad is one of the best sites for us as far as drought stress phenotyping is concerned, not just even for drought, but also for heat stress and waterlogging stress. We moved, thanks to again a public-private partnership that was championed through maize CRP, or CGI research program. We partnered with a company in Spain, University of Barcelona, and Crop Breeding Institute in Zimbabwe to develop this unmanned aerial vehicle called Skywalker. And this Skywalker can very effectively capture now the data from our drought and low nitrogen stress phenotyping experiments in Zimbabwe. We are planning to introduce one in Hyderabad too. There are, of course, challenges. First of all, as someone presented, I think Pat has presented yesterday, We do need permissions from the governments to fly these UAVs, otherwise you land yourself in trouble. The second most important challenge is how to manage, how to process and use this high volume data. The data that you can generate through these unmanned aerial vehicles is almost explosive. How do breeding programs manage this data, process this data, and use this data in selection decisions will be the key. That's again an area where there is an intensive opportunity for public-private partnerships. Is there any evidence of a successful adoption and impact of the varieties that we have brought out? Drought-tolerant maize for Africa is one such example. Now we have 180 drought-tolerant varieties released in sub-Saharan Africa since 2007, 60% of them being hybrids. And most importantly, 42,000 tons of this seed is produced by seed company partners, covering almost 2 million hectares in sub-Saharan Africa, which is a chronic drought-prone area almost once in every 3 to 4 years. And these materials benefit almost 3 million households. You can see here the relative distribution of our products going through a public sector as well as through private sector. Increasingly nowadays, more through the private sector channel. But there is a tremendous wave of products that have come since 2007, thanks to, again, the long-term commitment and support from some of the funding agencies, especially the Gates Foundation. Now, through the public-private partnership I mentioned earlier, the heat-tolerant maize for Africa, we have the first wave of hybrids that are ready for deployment in South Asia. These are the hybrids that will be channelized through not only public sector, but also the private sector, which are partners in this alliance. And plus, we gained from the double haploid lines that are developed by Pioneer and in-kind support made by Pioneer in the heat-tolerant source maize populations that were developed by CIMMYT under this partnership. Every year, this will continue to happen. So, once again, many thanks to Pioneer management for this excellent contribution. But enhancing genetic gains, we made such a huge progress through conventional breeding. Do we really require markers? Still, yes, indeed. We need to enhance genetic gains in maize from almost 1.6% to 2.4% in the coming decade. This can only be made possible through a very rapid translation of all these modern advances, be it high throughput and reasonably precise field phenotyping, breeding support, decision support system. John Marcel Ribot will talk about the breeding management system, mechanization and automation of breeding operations, doubled haploids, rapid cycle genomic selection for complex traits, and most importantly, again, year-round nurseries. CIMMYT's maize trait pipeline is indeed full. We have at various stages of discovery, validation, and deployment all these traits, whether it is in sub-Saharan Africa or Latin America or Asia. A recurrent theme you can see here is drought, a number of disease-resistant traits. But what is really important, I will focus on 3 major traits where we have made tremendous progress again through involvement of private sector. The first, of course, is developing maize streak virus resistance markers. This is, although private sector has not contributed to this, but this is perhaps the first success that we derived for developing breeder-ready production markers for MSV based upon a major QTL on chromosome 1, developed and validated through several studies earlier. This was fine mapped by Sudha Nair, who again sits here in CIMMYT India team. And this favorable allele was found to be absent in key drought donor lines. So it's a very, very important trait to in progress. And no maize variety in Southern Africa is released without MSV resistance. So that's the importance of the trait. We now have a haplotype based on 3 SNPs with a prediction efficiency of almost 0.94 and already currently in the product development pipeline. So we use these markers intensively. Genomic leads for maize nitrogen use efficiency has come through CIMMYT Pioneer synergy in a project called Improved Maize for African Soils, where germplasm is contributed by CIMMYT and partners in Africa. High throughput genotyping is done by the Pioneer team, Joint analysis of jivas and biparental population results by CIMMYT and Pioneer. And besides that, DH lines developed in CIMMYT's tropical and subtropical source populations. Almost 14,000 DH lines have been produced by Pioneer under this partnership. And markers and candidate genes have been developed through joint phenotyping and genotyping efforts. Seedling phenotypes were contributed by Pioneer. Field-based low nitrogen phenotypes were contributed by the CIMMYT's African team, and candidate gene discovery and validation and marker analysis was done again jointly by the Pioneer and CIMMYT teams. The WEMA partnership, the Water Efficient Maize for African Partnership, is another model public-private partnership of marker analysis and utilization in a big private breeding program. Monsanto is a key partner in this, along with CIMMYT and NARS from 5 countries in sub-Saharan Africa. This is perhaps the world's largest MARS and GS analysis in the tropical genetic backgrounds. And 34 populations, genetic gain studies completed for 18 populations, 10 under MARS, 8 under GS, compared with pedigree-based selections and using the best commercial hybrid checks to test the final products, including those from Pioneer and DeKalb and local seed companies. The average gain per cycle we saw through this intensive study undertaken in the last 4 years is almost 183 kgs per hectare under optimum conditions and 45 kgs per hectare under drought conditions. The gains in grain yield under drought and optimal environments across 10 Mars populations was indeed quite significant, almost 75% gain seen in, the Mars showed gain in almost 75% of the populations, but one important factor that needs to be noticed here is some populations may not show any clear advantage. So we do need to invest in the best populations when we talk about Mars and GS. So it may or may not be applicable across all genetic backgrounds. Gain in grain yield using GS also has been quite significant. This paper we published in Crop Science recently. But what are the lessons learned from these genetic gain studies? Mars and GS can provide almost 3 to 4 times higher grain yield compared to the pedigree-based selection without significantly affecting the plant height and the flowering behavior. However, extremely time-sensitive project requiring tremendous coordination, planning, and implementation. Gain is highly dependent on the cycle time, that is how quickly you complete the final cycle. And as I said, it doesn't work on all populations, so invest your efforts and energy on your best populations for such studies. We derived also products through these massive studies, fixed lines as well as drought-tolerant hybrids. The DH lines were once again contributed by Monsanto. Almost 6,000 DH lines have been contributed based upon the cycle 3 source materials. Intensively screened once again for production markers for MSV and for maize lethal necrosis. And several new single-cross hybrids are now based upon these very promising DH lines. This is perhaps the best integration of DH and markers in any major public-private partnership project. And now we have an opportunity to scale up the DH process in Africa. We have a state-of-the-art double haploid facility established in Kiboko in Kenya. And we offer now DH line development service both to NARS and SMEs using our tropicalized haploid inducers. Just in the first cycle, we have developed almost 60,000 DH lines in the very first year. Gary will be very happy to hear that. So this model is also now possible to replicate in Asia, so we are making intensive efforts in this direction. Let me finally, 2 minutes, talk about this major challenge called maize lethal necrosis. Gary recently says, please stop the hell in its tracks. So that's what we are trying to do. Why this? What is this hell? This is a viral disease caused by a combination of 2 viruses called maize chlorotic mottle virus and sugarcane mosaic virus. Just within 2 years, it has been reported in Kenya, Uganda, Tanzania, Rwanda, South Sudan, and very recently in Ethiopia, affecting in a major way many commercial maize varieties in Eastern Africa. all the progress that you make can become suddenly almost nullified if such challenges come up. So breeding should be geared up for this. You will see here 117 out of 119 commercial varieties in Kenya will show a response like this, devastated by this major disease. What do we do when it happens in a hybrid seed production field? If your male parent is susceptible, this is what is the result. The male parent is gone, so you will have zero yield in a commercial hybrid seed production field. It's not a new disease for maize, but it's a new disease in Africa. Highly virulent strains, conducive environment, seed transmission of MLN causing viruses, especially MCMV, is a major issue here, besides insect vector transmission, and only 10 to 15% of elite maize germplasm offering resistance to MCMV plus SCMV. What will you do if you encounter such a challenge? William Ward once said that the pessimist will complain about the wind, the optimist will expect it to change, but the realist will adjust his sails. So that's what we are trying to do now, adjusting our sails to tackle this challenge by, together with partners, establishing a centralized screening facility, intensive screening of germplasm, optimization of phenotyping protocols, discovery, validation, and deployment of genomic regions for MLN. And fortunately, there is hope. You still see such lines which are tremendously tolerant to the disease, while some of the lines are highly susceptible. This is a line from KSICRISAT University in Thailand showing an extremely good response besides some of the CIMMYT lines. And we already have hybrids in pipeline for this disease, just within 2 to 3 years. Almost 10 hybrids are now under various stages. 6 of them already recommended for release in 2015. Combining not only MLN tolerance, severity score is very low, as you can see here, coupled with grain yield under low nitrogen. We offer phenotyping service to private sector partners, including the large seed companies as well as small and medium enterprise seed companies. We have unraveled the genetics of resistance to MLN causing viruses recently using both GWAS as well as QTL analysis in biparental populations. We are deploying these markers in a large-scale marker-assisted backcross project involving 25 major lines that are used across the world, especially in sub-Saharan Africa. We are further dissecting these traits by analyzing the phenotypic responses against SCMV alone, MCMV alone, and MCMV plus SCMV. Final 2-3 slides. We need to move from markers to markets. Just discussing about markers is not sufficient. In the past, we measured our impact in terms of number of crop varieties. Now we have to talk about demonstrated impact in the farmer's field. Time to market of competitive products is the key. For that, partnerships are really important, especially with seed companies. In '96, we had 11 seed companies as partners. Now we have 98 seed companies. We formed a consortium in Asia again with both public and private sector partners called IMIC. Many thanks to colleagues, partners from worldwide, especially in Asia, Sub-Saharan Africa, and Latin America. Funding agencies which are shown long-term commitment for developing and deploying climate-resilient maize varieties, and CIMMYT colleagues, my strength for their dedication and commitment to the mission. Thank you so much.
Thank you, Dr. Prasanna, and we will take some questions. Please, who wants to go first? Yeah, there's one here in the front. Here, the third row.
There's one from the back there too.
I'm Sheshai from UAS Bangalore. Thank you, Prasanna. That was an excellent overview of what's happening in maize research in CIMMYT. Though I know a little bit about it through discussing with you, I'm very curious about the drought hybrids that you have developed. Other than the antithesis to silking interval, which is one of the most important traits, is there anything else that has been done?
Yeah, we have, that's a very good question. We have a set of 4 or 5 major selection criteria, not only ASI, but also on the basis of thermal imaging or NDVI. We also analyze the crop's response or senescence under drought stress environments. High throughput field-based phenotyping is again possible for this. That's what we are exploring through the Skywalker experiments. With high correlations with what we manually record intensively in the field conditions, we can reduce substantially this effort and energy through aerial remote sensing in the direction.
Thank you. There's one right at the back.
When you discussed about Mars and genetic gain, you indicated Mars doesn't work in all the population, and you advised to invest on the best population. What do you mean by the best population?
Absolutely. When we analyzed using almost 18 populations, as I said, Mars worked well in only 75% of these total populations. What's the reason for that? Why those 25% respond as well as those 75% is something that we are now analyzing through our physiology team. But what is really important is the complementation and the diversity that is there in your populations. If it is too huge, then possibly the gains are very limited. So therefore, what is really important is selecting the best populations based upon clear understanding of the drought-tolerant response profiles of your parental lines is key. Raman Babu did this analysis recently at CIMMYT India by profiling some of our best drought-tolerant sources using markers for major QTLs that have consistently expressed across several populations. That understanding of what are those constitutions of genotypes that contribute to drought responses is perhaps the key. We haven't done that deliberately for many years, but markers do provide an opportunity to dissect which lines or which donors to possibly use when we talk about constituting biparental populations.
Thanks. There's one last question from Dr. Bhatia.
You showed the average gain per cycle. I just want to know what's the cycle time?
Yeah, this is a good question. The cycle time, we have used 3 cycles here. Cycle 0, cycle 1, cycle 2, cycle 3. Cycle 0 is based on both phenotypic and genotypic data, advancing from cycle 0 to cycle 1. But cycle 1 to cycle 2, cycle 2 to cycle 3 is only based upon genotypic data. So no phenotypic data is involved. Therefore, we cut down on the cost of that. But what is important, cycle time, is how many seasons you complete per year is also really important. How far you can move towards 3 seasons per year. If we can move towards 3 seasons of breeding per year, then I think genomic selection will make a huge impact. But in many of the African contexts, getting to even 2 seasons per year is quite tough. So that is one bottleneck that we are trying to overcome, especially in light of this intensive problem with maize lethal necrosis in Africa. But if you can move from even 2 seasons to 3 seasons, genomic selection will make a huge impact.
Thank you, Dr. Prasanna, for the nice presentation.